Well, welcome back to the afternoon session, everybody. Welcome in particular to all our young investigators who provide all the energy in the meeting, and welcome to our distinguished visitors, and welcome to all those who are watching online. So I'm pleased to introduce Gong, who's going to talk to us about homotopy types of toric orbifolds from Weyl polytopes. Well,
thank you, Tony, and thanks for organizers and the audience. Okay, so that's a topic, and there will be 4 sessions in this lecture. So the first main result, Weyl groups Wx linearly and the real Euclidean space V, and P is the convex hull of the W orbit of a point in V, and the P and the quotient of P are both polytopes lying in V. Hence, there are 2 associated toric varieties, XP and X of the quotient. Our result is there is the homotopy equivalence from the quotient of the variety to the variety of quotient for LED type. So for Ilurex, in 2015, Mark Bloom showed that the 2 are isomorphic as varieties for Lie types ABC. And in 2021, Horiguchi, Masuda, Shoshine, and Song, Masuda and Song, they are here in audience. They show that for Lie types ABCD, there is a rational cohomology isomorphism for any parabolic subgroup WK. And also, John-Ping generalized this isomorphism to symmetric polygons. Second example first. So we consider the example of Lie type A1. So in R1, the Weyl group action is given by the reflection that maps X to its negative. We consider the Weyl polytope, which is the interval from -1 to 1. And hence, the quotient polytope is the interval from 0 to 1. So the see those pictures below. For the toric variety of XP, we considered it is S2 embedded in R3. And what's induced the Weyl group action on it? It's written in blue. So it maps a point XYZ to -X, -Y, and Z. So it is just the array or rotation along the Z-axis by degree pi. So it maps the left hemisphere of S2 to the right hemisphere. And the action on the boundary circle, it is just a mirror reflection. So it maps the boundary circle into an interval in the quotient. I draw out the picture in the middle. That's the picture of the quotient space. We can say that it is actually homeomorphic to a sphere. And for the toric variety of the quotient polytope X of P over W, it is again a sphere here. And what is our map phi? It is actually collapsing the red vertical line into a point 0. So we get this map phi. It is clearly that this map phi is surjective, and it is the homotopy equivalence from a sphere to a sphere. That's an example. Now the second part, construct toric varieties from polytopes. So given a lattice M of rank n, and its dual lattice M, we consider the 4-dimensional lattice polytope P in the real span of M. And consider each facet F of P has a normal vector L considered in the real span of M, and which has to be integral, primitive, and pointing inside the polytope. And we define the normal fan sigma P, whose coordinates are generated by the sets of normal vectors whose correspondent facets have non-empty intersection in the polytope P. And each coordinate in the normal fan corresponds to an affine complex toric variety, and those affine pieces fit together to form the algebraic variety XP. again, an example. So in R1, we consider the polytope P, which is the interval from -1 to 1. And the normal file of P consists of 3 coins, the 0.0 and the positive ring and the negative ring. And the correspondent affine pieces are C, C star, and C respectively. And they fit together to get this toric covariance XP. So we can see that this colimit is actually homomorphic to S2. Okay. We also have a topological description of this toric covariance. So we constructed the topological model via the moment map. Define Sn to be the real span of M mod the action of translation by M, which is also the tensor product of N and S1. So here is an Sn equivalent homomorphism that XP is homomorphic to the quotient of the product Sn cross P. And here T1 P1 is equivalent to T2 P2 if and only if P1 is equal to P2 and it is lying in the relative interior of some phase F. And the T1, T2 are congruent modulo the subspace of the torus spanned by normal vectors correspondent to F. Here is an example. So consider the polytope, the interval -1 and 1 in R1. First, we constructed the product space, which is the S1 cross the interval. And here, I embed the interval inside the cylinder. And to get the quotient, we need to quotient those torus corresponding to facets. So the blue circle is collapsed into the point -1, and the red circle is collapsed into the point 1, and hence we get a quotient S2, which is the topological model of the toric covariance of the interval. Okay. Now, group action. So suppose that a group has an action on the lattice, and it has an induced action on the polytope P, and hence the group acts on the normal fan and on the toric covariance. We have the following lemma that says for any G of the group, the following diagram is commutative. This lemma simply tells us that the topological model construction is G equivalent. Okay. Third part. And what is a root system? A root system is just in an n-dimensional real Euclidean space V, a finite set R of non-zero vectors is a root system if it satisfies the following 3 conditions. 1, if alpha is a root, then its negative is also root, and only those 2 multiples are roots. And 2, for 2 roots, alpha beta, S alpha beta is actually, okay, S alpha is just the reflection by the hyperplane whose normal vector is alpha. So S alpha beta is just the reflection image of beta. And 3, the reflection coefficient has to be an integer. And a root system always have a basis. It's called a simple system, such that each root of alpha can be written as a unique linear combination of simple roots. And in this lecture, we usually think R, the root system, to be of rank n. That means we have n simple roots, alpha 1, alpha 2, up to alpha n. And the Weyl group is defined to be the group generated by those simple reflections. And a subset I of n, it can determine a subgroup of the Weyl group. It's called the parabolic subgroup, and it is generated by those simple reflections indexed by I. Sorry. This is an example. So this example is an example of Lie type A2. We consider the space V as a subspace of R3, whose normal vector is 1, 1, 1. And we consider vectors alpha 1 to be 1, -1, 0, alpha 2 to be the vector 0, 1, -1. And see the picture. And in the picture, I draw out 6 roots of this root system. One can say H1 is the hyperplane normal to alpha 1. H2 is the hyperplane normal to alpha 2. And H2 maps, the reflection of H2 maps alpha 1 to alpha 1 plus alpha 2. That's the simple reflection. And so one can say S2 alpha 1 is just the alpha 1 plus alpha 2. So the reflection coefficient is 1. And one can also check that the Weyl group generated by the 2 simple reflections is isomorphic to S3 that permits the coordinates of R3. One can say that the Weyl group has an action on the lattice generated by roots. Okay. Now we define the fundamental chamber C, which is a set of vectors that is on the same side of each simple root. Here is a theorem I just copied down from a book of Harvey's. It says that the closed chamber is a fundamental domain for the Weyl group action on V. That means each W orbit intersects the closed chamber for only one time. And we fix a point in the open chamber and define the Weyl polytope to be the convex hull of the W orbit of V. And hence the quotient P mod W is just homomorphic to the intersection of P and the closed chamber. The intersection is again a polytope. Let's say an example. Still, the example of Lie type A2. In the first picture, we have already seen those roots. Here, the brown area, it is on the same side of alpha 1. It's again on the same side of alpha 2. So it is the fundamental chamber. And in the second picture, I drew the pictures of polytopes. So we choose a point A in the open chamber, and it is convex hull of orbit is our Weyl polytope P. And the intersection of P and the fundamental chamber is the quotient polytope P mod W. Okay, now let's have a look at the phase structures of the 2 polytopes. For the Weyl polytope, one can say those 3 black edges are conjugate, and those 3 red edges are conjugate. So in general, we can say that the 2 facets intersecting the closed chamber generate all faces of the Weyl group by intersection and the group action. Okay, now let's have a look at the phase structure of the quotient polytope. It is enclosed by the 2 generating facets of P and the H1 and H2. So it is a cube. It is a 2-dimensional cube. It's a square. Okay, so in general, we have this result about phase structures. Let HI to be the convex hull of A under this maximum proper parabolic subgroup W sub n minus I. One can say all those Fi's are those facets of P meeting the closed chamber. So they are the generating facets. And let HI to be the hyperplane normal to alpha I. So in the first lemma, I just give out the description of faces of P, which just tells us that all those generating faces that meet the closed chamber generate all faces of P by intersection and the Weyl group action. Here I choose C from the coset just to kill the trivial action of the isotropy subgroup. Okay, and in the second lemma, it's about the face of the quotient polytope. In this lemma, it just tells us the quotient polytope is an n-dimensional cube, and the phase supported by HI is opposite to the phase supported by FI. That's the idea behind this lemma. So I just write HIFJ to be the intersection of those faces and it gives out faces of this quotient polytope is IJ range among disjoint subsets of N. The idea behind it is just that this quotient polytope is a cube. Okay, for early works, Weinberg studied the phase structure of the Weyl polytope, and Barul, Guihu, they studied that of the quotient polytope. And the 21 paper, again, HMSS, they studied the phase structure of the quotient polytope for Lie types ABCD and for parabolic subgroups. Okay. Now we need to construct the homotopy equivalence. First, we need to choose lattice to construct the toric variety. So we need net M to be the lattice generated by roots, and the N is the dual lattice. We call it the lattice of co-weights, and we write omega I to be the basis dual to alpha I. And we choose a lattice point contained in the open chamber, and we consider the Weyl polytope in the real span of M, and its normal vector in the real span of N. Both spaces are V, but with different lattice structures. And for the notation, we write sigma for a coin in the normal fan of P, and the sigma sub P for a coin corresponding to a face of P whose relative interior contains P. Similarly, we define sigma sub N and sigma sub NP for the normal fan of the quotient polytope. Okay. And here is the lemma that gives out an equivalent description of the quotient of the variety. So it says that identify XP with the union indexed by point from the Weyl polytope of tori. Then the quotient is homomorphic to the quotient of this product. Sn cos P intersecting the closed chamber. And here T1 P1 is equivalent to T2 P2 if and only if P1 is equal to P2 and they are lying in some minimal phase HIFJ of the quotient polytope. And T1, T2 represent the same elements of this quotient under the WI action. So here is the idea behind it. So for an index point outside the closed chamber, it is conjugated to a point in the closed chamber. So in the quotient, we can consider it in this quotient. That explains this intersection. And when P1 when the index point P lies in some HI, this index point, it is fixed by the reflection of this hyperplane, but the action is non-trivial on the correspondent torus. And in the quotient, we should consider this quotient. That's the idea. But let's say an example again. So we consider the example of Lie type A2. We have already seen the picture of this Weyl polytope of Lie type A2. And for the toric variety, we observe this variety via its projection onto the polytope. So at the point P1, there is no normal vector at this point. So the torus at this point, it is Sm mod 0. It's just the Sm. And at P2, the normal vector at P2 is omega 2. So the torus at this point should be Sm mod the subtorus spanned by omega 2. And similarly, the torus at P3 is the torus Sm mod the subtorus spanned by omega 1 minus omega 2. Okay, and how can we get the quotient? Okay, so in the quotient, the torus at P3 is conjugate to the torus at P2. So in general, we can just consider the index points in the quotient polytope. Okay, let's see what is the space at P2 in the quotient. In the Weyl polytope, P2 is fixed by the reflection of H1, which is a group of W1. But the W1 has a non-trivial action on the torus at P2. So in the quotient, we should consider the torus at P2 should be the quotient of this torus mod the action of W1. Similarly, in the picture, at the point of P1 of the Weyl polytope, this P1 is fixed by the whole Weyl group, but W has a non-trivial action on this torus Sn at P1. So in the quotient, the torus at P1 should be the quotient of Sn on the W. That explains the idea how to construct the equivalent description of this quotient of XP. Yeah. Now we need to construct the map phi. Here is the following commutative diagram. The triangle, the top map is just the deflation of the topological model of the variety of the quotient polytope. And the left map is just the deflation to construct the equivalent description of the quotient. And we get this map phi, which is surjective due to the universal property of the quotient maps. Okay. Now we need the lemma from Snell. It says that suppose X, Y are compact simplicial complexes. F is surjective, is mapped from X to Y. And each fiber is K-connected and locally K-connected. Then the induced homomorphism on the homotopy groups is an isomorphism for the degree less than or equal to K. And it is down to for the degree equals K plus 1. Okay. In our case, this map phi, the target space and the domain space, they are both compact simplicial complexes because one is a variety and the other one is a quotient of a variety. So to show this map phi is a homotopy equivalence with the help of the result from Snell, it is enough to show that each fiber of phi is contractible and locally contractible. Then we can see that this map phi induces an isomorphism on the homotopy groups of all degrees. So phi is a homotopy equivalence. So I want to emphasize again, the remaining work is to show that each fiber of phi is contractible and locally contractible. Okay, let's see an example again. The example of Lie type A2. So in the first picture, we have already seen the equivalent description of the quotient. So the quotient at Q1, the torus should be Sn mod W. And at Q2, the torus should be Sn mod W1. And in the second picture, that's the space, that's a picture description of this variety of the quotient. At Q1, there are two vectors at Q1. So the torus at Q1 should be Sn mod Sn, which is a point. And at Q2, the normal vector at it is alpha1. So the torus at Q2 should be Sn mod S alpha1. And this map phi is given by this natural quotient map. It maps the torus at Q to the torus at Q. So, so it maps the torus at Q1 to the point at Q1. It maps the torus, this quotient at Q2 to this quotient at Q2. We know that it is surjective. And what are those fibers? Is the two examples. So the fiber at TQ1, which is just a point. So the fiber at this point here is just the Sm mod W. And what is this quotient? Which I will show you later. It's just a quotient of a triangle by the Demo-3 action. This action is given by the permutation of vertices. So it is just homeomorphic to a disk D2. And the fiber at this TQ2, we take E to be the unit of the torus. So fiber of EQ2, it is just the SQ1 mod omega W1 action. So this quotient, we have already said this quotient in the example of D-type A1. It is just a torus by the mirror reflection. So it is just an interval. In this example, we have already said these two fibers are both contractible and locally contractible. And what are other fibers? Here is the lemma. Suppose that TQ is a point of the fibrity, TP is a point. And P lies in the relative interior of some phase HIFJ. Then the fiber is contractible and locally contractible. More precisely, we can give out the homeomorphism type of the fiber. For this fiber is homeomorphic to the quotient of this torus. We can get this quotient by following the commutative triangle early. And again, we can observe this quotient on the level of Lie algebra. We get the third description. And as for the proof of this lemma, I just want to tell you about the case where I is equal to M. As for other cases, the proof is similar. So in this case, the fiber TP is just a Sm mod W. And we observe in the level of tangent space, it's just this quotient. The top thing is the closed alcove, and the bottom thing is the co-weight lattice over the co-root lattice. I didn't give out their definitions, but here is the fact that the top thing is a polytope, and the bottom thing is a finite group of affine transformations. And for this quotient, it is easy to show that it is contractible and locally contractible. So that finishes the proof. As for generalizations for subset K of M, this parabolic subgroup WK has an action on the Weyl polytope, and the quotient P under WK action is again a polytope contained in V. We have this result. There is a homotopy equivalence between the quotient of XP under WK action to the toric variety of this quotient polytope. And here I want to end today's lecture with this question, which was also mentioned in the paper 21. Again, HMSS. Is there any other isomorphism between the two objects? That's all. Thank you.